Hello everyone and welcome to Growing 5.4. Today's learning target, I will be able to perform operations with the scientific notation. Our ACES questions assignment down here for 5.4, beginning on page 92, is 39 through 42, 45 through 49, 51 through 61 odd, and 64 through 65. Now, if we turn into page 84 in our textbook, we're going to come up with operations with a scientific notation. And what they're going to use as the example here is water and how much water we use each day for each person or each country or various different things. They talk about gray water and what that is. You can read through that. But if we get down here into the numbers, we're looking at a total of approximately 4.1 times 10 to 11 to the 11th power gallons of water is used each day in the U.S. Well, some of that water is used for cooling electric power plants, and those demands are 2.01 times 10 to the 11th power of gallons per day. Irrigation uses 1.28 times 10 to the 11th gallons of water per day, and livestock consumes about 2.14 times 10 to the 9th gallons of water per day. So it's a lot of water. These would be big numbers if we put them in standard form, but let's think back to what we've learned about scientific notation and how many decimal places our exponents are telling us that we will be moving, and that should give us some indication of how large a number is. Now we're going to be doing multiplication, division, adding, and subtracting in scientific notation, and some of you may look at that and go, I'm a little worried about that. Well, actually, it's fairly easy because notice that this is written as 2.14 times 10 to the 9th and times 10 to the 11th or times whatever. The base is the same in all scientific notation. The base is always going to be 10. Okay, so it's going to be easier to apply the rules we've learned about exponents. Both integral and rational exponents are going to apply here, and the base for all scientific notation is 10, so that should make things a little easier for you. So one of the things we might think about is which of these is greater, the amount of water used for irrigation or the amount used for livestock. And how might you find that out? Remember, looking at our scientific notation should give you an indication of how large or small the numbers are, and more easily be able to tell which one of those is larger. Excuse me. So as we go on to page 85 and start to take a look at our problem for 5.4, it says Gary and Judy are studying water use, and they need to figure out how much water is used per person each day. U.S. population in the same year was approximately 301 million people. Assume that everyone uses the same amount of water each day. How much water is used per person each day? So if we look down here in part A, and actually I'm going to flip to the next page because I have it blown up a little bigger. It says Gary and Judy are figuring out how much water each person uses per day. And they're both going to come up with the same number, but they have two different methods. So I would encourage you to take a look at this, make sure you can understand how each of them came up with their method. And then you can go ahead and use whichever one you prefer to finish the rest of the problems and move forward with our scientific notation investigation here. So it says they use the following expression to find their answer. 4.1 times 10 to the 11th, okay, that's how much overall water was used, divided by 301 million people. So each of them used a different method for carrying out the calculations. Consider the two methods for solving the problem. Well, Gary went ahead and thought of both numbers in millions. 10 to the 6th is 1 million, so he changed both of them to be to the 6th power, okay? So instead of 4.1 times 10 to the 11th, that becomes 410,000 times 10 to the 6th, just by moving the decimal place 5 places. He then went ahead and divided them, 410,000 divided by 301, both of the numbers in front of the times 10 to 6. He got 1,360, so that's his results. Judy, on the other hand, converted the 301 million to 3.01 times 10 to the 8th, then rewrote the problem as 4.1 times 10 to the 11th divided by 3.01 times 10 to the 8th. And you can break these apart, and I'll show you how to do that a little later. 4.1 divided by 3.01 is going to be 1.36, and 10 to the 11th minus, or divided by 10 to the 8th, is 11 minus 8, or 10 to the 3rd. So if we rewrite that, it is still 1.36 times 10 to the 3rd gallons per day for each person. So now that I've read through both of these for you, let's take a little closer look at how they were able to come up with their calculations and the way they went about it. So for Gary's method, to come up with 410,000 times 10 to the 6th, what he had done to go from 4.1, where the decimal was here, he went and moved 1, 2, 3, 4, 5 decimal places, and now the decimal's here. That's how he came up with 410,000. Well, we know with our rule of exponents that if we have the same base and we subtract, we can find out what our other exponent is. So we had 11 decimal places that we had gone, and we subtracted 5, so now we are left with 6. And so that's how he came up with 410,000 times 10 to the 6th. And how he changed 301 million to the 6th is he started here, 1, 2, 3, 4, 5, 6. So he was left with 301, which gives you your 301 times 10 to the 6th. And then he wanted to divide, because we're taking the total amount that was used, the 4.1 times 10 to the 11th, and we're dividing it by 301 million people, which gives you 1,000. If you go ahead and do the math here, that will give you 1,360 gallons per person per day. Right? Now, Judy's method is she went ahead and took the 301 million and converted it fully to scientific notation by moving it the decimal 8 positions. There's 1, 2, 3, 4, 5, 6, 7, 8. So we're left with 3.01 times 10 to the 8. Then she decided to do her division a little different way. She took the 4.1, and we broke it apart, because we're able to do that because on top and on the bottom are each multiplying. So with our rules of math, we're able to break these apart into two separate areas and take 4.1 and divide it by 3.01 to get 1.36. And then for 10 to the 11th divided by 10 to the 8th, we just use our rules of exponents and take 11 minus 8. So if we were to rewrite this, we would be 10 to the 11th minus 8, okay? And that's going to equal 10 to the 3rd, okay? 10 to the 3rd. So that's how we come up with this part. 4.1 divided by 3.01 is 1.36, okay? And so you may be saying, well, this came up with 1.36 times 10 to the 3rd. How is that the same as 1,360 gallons? Well, if we come up with 1.36 times 10 to the 3rd, that means for standard form we need to move the decimal to the right 3 places. So if we move it 1, 2, that's not far enough, so we need to add a third, or a 0 to move it a third spot. So there we are, and that's where we come up with 1,360. Hopefully that helps you see how our exponential rules still apply in scientific notation. Go ahead and work through parts B, C, and D, getting you some good practice with those. I'm not going to show you examples of those. I want you to go ahead and use what we talked about here and what you already know about exponents to try to work through B, C, and D. If you have questions, then in class, please let me know, and we'll conquer those as they come up. Once you're through that or have a solid understanding of the scientific notation and its rules, then go ahead and jump into the ACES questions for 5.4. Beginning on page 92, we'll go 39 through 42, 45 through 49, and the odd numbers of 51 through 61, and finishing up with 64 through 65. That'll do it for 5.4. Let me know what questions you have and what challenges await us in the class.